This is Professor G. Kumar, Professor of Geology, BIT Sindri. In fact, I did my MSc from Patna University in Geology in the year 1978, and then I was appointed as lecturer in Ranchi University in the Department of Geology, where I served for nearly 1 decade, and in between I did my PhD from Delhi University, Department of Geology in the field of oceanography or marine geology. I also did my postdoctorate from Delhi University, and on both occasions I got the fellowship from Department of Ocean Development, Government of India. I participated in several cruises in the Indian Ocean as well as in the Pacific Ocean, and till date I have produced 6 PhD under my guidance and more than 100 research papers, besides organizing nearly 40 short-term course, training program, etc. at various places on national level and as well as on international level. I have thoroughly traveled many countries such as US, UK, France, Germany, Switzerland, and some of the other European countries. But I have excelled in the field of oceanography in both Indian Ocean as well as in the Pacific Ocean. Today I will talk about the hydrothermal deposits of the sea floor and particularly along the mid-oceanic ridges. So far you know that the plate tectonics concept, it has 3 regions, the mid-oceanic ridges, the subduction zone and the transform fault. In the mid-oceanic region, the new crust is being continuously created, whereas in the subduction zone, the sea floor is consumed once again into the mantle, and transform fault is the lateral sliding of the 2 plates across each other. I will be confined along the mid-oceanic ridges because it witnesses many important deposits because of the fact that ridge concept has been given because that area is slightly elevated and in comparison to the adjoining areas because of continuously coming of the materials from beneath. The sea floor in fact offers a variety of minerals, many of which are considered to be alternative sources of metals in the future, and as such the hydrothermal sediments along the active spreading centers are the future source of important mineral deposits. Hydrothermal deposits are formed by the interaction of the sea water with the submarine volcanic activity. The hydrothermal fluid that gushes out of the vents on the seafloor deposit many metal sulfides, iron, copper, zinc, lead, oxides, iron, copper, and sulfate, barium and calcium minerals. The sediments close to the vent are enriched with high content of iron, manganese, silver, chromium, lead and zinc. The mid-oceanic ridges form the site along which the new oceanic crust is being created. It forms the largest single unit of the earth crust consisting of nearly 72,000 kilometers and 25% of the entire globe. Among the outstanding questions is how many deposits might be accessible to the deep sea mining. More than 300 sites of high temperature hydrothermal venting have been identified since the discovery of black smokers, but significant massive sulfide accumulation has been found at only one of the 165 of other sites. Its estimates of total number of vent fluids associated mineral deposits based on bloom studies and deposit occurrence models range from 500 to 5,000. The total accumulation in these areas is estimated to be 6 into 10 to the power 8 tons, containing 3 into 10 to the power 7 tons of copper and zinc approximately. Now I would like to talk about the historical background of the discovery of the metal sulfides along the mid-oceanic ridges. The discovery of submarine hydrothermal vents at the Galapagos Rift in the year 1977, the first black smokers at 21 degree north east at 21 degree north latitude at East Pacific rise in the year 1982. More than 50 sites of hydrothermal venting and seafloor massive sulfide deposits were known on the midoceanic ridges by the early 1990s. More than 150 sites has been discovered till 2000. Significant accumulation of metals from hydrothermal vents are found in the oceans, such as metalliferous sediments in the Atlantis too deep of the Red Sea, where the deposit is of the order of 91.7 into 10 to the power 6 tons of 2.06% zinc and approximately 0.46% of the copper. Even more metal rich is contained in manganese nodules. The global resource of copper in nodules has been estimated at 7 into 10 to the power 8 tons, and a number of countries including China, Japan, Korea, Russia, France and Germany are actively exploring for nodules in the Pacific. The first deep sea mining of base metals will likely to be formed the much smaller higher grade massive sulfide deposits in the new volcanic zones of ridges, volcanic arcs and back arc basins. One commercial company has already been granted a license to exploit massive sulfide deposits in the Bismarck Sea of Papua New Guinea. These figures indicate the gushing out of the 3-meter high chimney, and another figure is close up of smoking chimneys 30 to 50 centimeter in height. Again, this figure indicates the hydrothermal smokers along the seafloor. Seafloor massive sulfide history, I would like to point out that in 1965, metal enrichment noted in sediments on East Pacific rise. In 1977, first seafloor massive sulfide inactive discovered in Galapagos Rift, that is also in the East Pacific. In fact, along the midoceanic ridges, we have two types of ridges, one where the active spreading is going on, which we consider as the active ridges, and where there is no spreading, we call it inactive ridge. The entire East Pacific rise belongs to the active ridges, whereas the 90-degree east ridge just south of India belongs to the inactive ridge because there no spreading is going on presently. In 1986, first SMS in a subduction setting, that is Manas Basin polymetallic nodule. In 2005, first commercial SMS survey, that is again in Manas Basin. In 2013, first SMS mine Nautilus. This figure indicates the spreading centers all across the world, and it constitutes nearly 72,000 kilometers. It passes through the Siberian, Arctic, Norwegian, Greenland basin, the Central and South Atlantic, the Indian Ocean, with one branch passing into the Gulf of Aden and other passing as the Pacific Antarctic ridge between Antarctica and Australia, New Zealand, eventually forming the East Pacific rise. In the Southeast Pacific, the East Pacific rise is linked to two other ridges, that is the Galapagos and Caucasus, before passing northward into the Gulf of California. It is assumed to continue beneath the Basin and Range province of the western United States and then links to the Juan de Fuca ridge of Vancouver, which eventually disappears beneath Alaska. The characteristics of the mid-oceanic ridges are that they occur within the pelagic plains. Consequently, whenever sediment deposits occur on them, they are of the pelagic nature. Pelagic means the deep sea deposits. However, the significant difference lies in the carbonate content. Quite often, the ridges lie above the carbonate compensation depth. Therefore, geochemical and sedimentological investigations of such deposits offer new problems. During the last few years, it has been established that the active oceanic ridges and other spreading centers are the locus of intense hydrothermal activity, as the Galapagos spreading centers in the Pacific, the East Pacific rise crest at latitude 21 degree north, 13 degree north, 18.5 degree south, 20 degree south, 23 degree south. In this figure, the hydrothermal sites have been shown at the different oceans. Again, this figure indicates about the global distribution of seafloor hydrothermal systems and related mineral deposits. There is information of 554 sites of seafloor hydrothermal activity, confirmed and unconfirmed, and inactive deposits. About 300 are sites of high temperature hydrothermal venting, 165 are confirmed sites of massive sulfide accumulation. This figure indicates the crustal plate boundaries, the spreading center and the subduction zone. As I explained earlier that we classify the spreading center into two types, that is the slow spreading, where the spreading is less than 4 centimeter per year, and the fast spreading, where the spreading rate is more than 4 centimeter per year. And this table indicates the characteristic feature of both these areas. The covering area for the fastest spreading is 28,000 kilometer, which is about 44% of the total ridge system, whereas the slow spreading, it has 44,000 kilometer, which is about 56%. Inferred depth of magma chambers beneath and the axial zone of volcanic extrusion 1 to 3 kilometer below in the fast spreading center, and 5 to 10 kilometers in the case of slow spreading center. Axial low velocity zone, yes, it is present along the fast spreading center, and it is absent in the slow spreading center. Micro earthquake focal depth maximum 3 kilometer along axis, and in slow spreading it is maximum 10 kilometers along axis. High temperature 300 to 350 degree centigrade hydrothermal activity is commonly observed in the case of fast spreading, but it is not observed as yet because it occurs at a deeper level. Axial new volcanic zone, in the fast spreading center, high degree of activity along strike and echelon for the intermediate rates, and in the slow spreading it is highly discontinuous. Transform fault spacing 90 kilometer on an average along the fast spreading, and 50 kilometers only in the case of slow spreading. Maintenance of transform fault pattern, unstable for small offsets, the spreading centers in the fast spreading zone, and stable for small offsets, spreading centers in the slow spreading center. Propagating rifts are common in fast spreading, and it is rarely in the case of slow spreading. Petrographic data, there is the steady state of magma chamber in agreement with the most geophysical data, and in the case of fast spreading, whereas the steady state magma chamber is in conflict with most geophysical data in the case of the slow spreading. Present example of early stage of opening is Gulf of California for the fast spreading, and the advanced stage of opening is the East Pacific rise for the fast spreading, and for slow spreading, early stage of opening is the Red Sea, Mid-Atlantic ridge is the example of the advanced stage of opening. Three characteristic types of metal-rich deposits have been identified in contemporary high ridge crest environments. So these are iron manganese rich, which is pure MnO2, and the iron sulfide rich manganese depleted. This figure indicates the type of the hydrothermal deposits. In fact, what happens that if the material which is coming up is concealed below the sea floor, then in that case we have the sulfide deposits, and in that case we consider it as the pre-discharge deposits, whereas when it is coming upon the surface, it is called the post-discharge deposits, and if it is near the vent, it is concentrated post-discharge deposit, and if it is away from the vent, then it is known as post-discharge diluted deposits. In the post-discharge deposits, we have concentrated and diluted, both types are there. Among the concentrated deposits are metal oxides, hydroxides, which are hematite, todorokite, delta manganese oxide, and among the diluted are metal silicates, stratified metal sulfides, metal oxides and hydroxides, and the common minerals being sphalerite, chalcopyrite, pyrite, barite, anhydrite, manganosiderite, goethite, hematite, barnesite, todorokite and manganese oxide. In cinch discharge deposits, we have massive sulfides, oxide and hydroxides and silicates, and the common minerals are sphalerite, pyrite, chalcopyrite, barite, pyrrhotite, urzite, anhydrite, magnesium hydroxyphate, goethite, barnesite, todorokite, delta MnO2, iron smectite, talc and silica. In pre-discharge deposits, we have the stockwork disseminated massive sulfides and disseminated massive oxides. Whereas in the intra-sedimentary deposits, we have massive sulfides and massive oxides and hydroxides. The pre-discharge type, which sometimes form the immense massive sulfide deposits, forms well before the discharge of the solutions through the sea floor. Whereas in the case of the cinch discharge deposits, it consists of deposits formed when the hydrothermal fluids are discharged through the sea floor at the end of their convective circulation within the crust, thereby precipitating much of iron and manganese oxides and hydroxides due to sudden drop in temperature and pH change. Lastly, the metals which are not deposited are carried out to the bottom of the sea water and later on deposited as post-discharge deposit in the form of concentrated oxides and hydroxides, silicates, sulfides, etc., or diluted, which is co-deposited with other terrigenous, hydrogenous or biogenic processes. Now, I would like to talk about the nature of the active rich sediments. These sediments in areas of high heat flow and fast spreading are quite enriched in iron, manganese, boron, vanadium, uranium, arsenic, mercury, cadmium and depleted in silica, aluminum and titanium. This is very characteristic in contrast with the terrestrial deposit. In the case of the terrestrial deposit, which are commonly very high in silica and aluminum content, but along the midoceanic ridges, silica and aluminum are quite deficient. These sediments are first to form on newly generated oceanic crust and appear to form the basal sediment layer on a spreading ridges. Only a small quantity of aluminum and titanium are derived from hemerolysis. Hemerolysis is the weathering of seafloor basalt, whereas their major source is terrigenous, means land derived. The submarine volcanism incorporates insufficient aluminum and titanium. The active ridge volcanism with maximum intensity provides iron and manganese and some other elements at rates that is higher than any other place in the ocean except close to the land. Reducing environment, turbidites and climatically controlled sedimentation processes are not operative on the active ridges area. The active ridge favoring reducing environment for their deposition. Iron and manganese oxides more readily than nickel and cobalt and should therefore precipitate first. The iron and manganese distribution on the active ridge show similar trends in which iron deposits before manganese. The rare earth studies and mercury and uranium distribution pattern suggested a seawater origin for these elements. Isotopic studies of the active sediments also signify that a large fraction of the trace constituents in such sediments derived from seawater adsorption. Degree of subsurface dilution is a major determinant of the final chemical precipitates. Low dilution leads to sulfide deposition, whereas intermediate one leads to iron sulfide deposition. Manganese remains unaffected because of its very low oxidation kinetics. Hence, a wide range of iron by manganese ratio is to be expected. The spreading rate and chemical composition of the active rich sediments show a distinct relation. This figure indicates at the x-axis spreading rate per centimeter here, and at the y-axis Fe plus Mn by Al, and we almost get a straight line equation for that. This figure indicates the track record of the cruise SO26 along the East Pacific rise. We started from the equatorial Pacific, from Lima, that is in Peru, and then we had the traverse along the equatorial Pacific. Then we took the northward journey up to 15° north in the Pacific, and then further we returned from the same location and sailed up to nearly 30° south. This indicates about the active plate movements in the area of East Pacific rise. Some of the very important plates where the spreading are going on, these are Caucasus plate, Nazca plate, South American plate, Juan de Fuca ridge, and the other continents like Australia, Antarctica, South America, North America, etc. Area A, you can notice that it is very near to the vent. Vent is shown by the circular section, and this is the bathymetry map of area A sediments, that is in 23° south latitude. Area B, that is the bathymetry map of area B sediments. You can notice that the vent is located at a water depth of nearly 2800 meters, and this area is slightly far from the vent compared to the previous area. Both these areas A and B are shown in this figure, where the sedimentation rate has also been discussed, and notice that in these two areas the sedimentation rate is of the order of 3 to 10 millimeter per 1000 years. Now I am coming to hydrothermal vent formation and formation of the sea floor massive sulfides. Once the seawater interacts with the basalt, the chimney begins to form. The following steps detail the growth of black smoker chimneys. Anhydrite calcium sulfate precipitates. The anhydrite forms a sheath around the existing fluids that are released from the crust. Development of anhydrite deposits grow up to 30 centimeters per day, forming the chimney's wall and insulating the hydrothermal fluids. Deposition of chalcopyrite or other metals. Pore spaces of the chimney become filled with anhydrite and other sulfide minerals. Anhydrite dissolves into the seawater from the outer wall of the chimney. Other chimney-like structures may form, such as beehive, and flanges can grow which are horizontal from the sulfide mounds. The structure can continue to grow up to the heights of 10 to 20 meters even. When hot fluids cease to flow, the metal sulfides begin to oxidize. The oxidation causes the chimneys to become unstable, and chimneys lacking siliceous, barite or calcites are also fragile, and therefore tectonic activity will cause the chimneys to fall. Ultimately, hot fluids cease to flow through chimney structures, either from the chimneys falling and sealing off the orifice, or from the lack of the fluid from the earth's crust. Here the comparison of area A, area B sediments have been given, and these are compared with the Pacific deep sea clay, which is known as the Pacific pelagic clay. The red color indicates the characteristic difference of area B and A and B sediments. A sediment, it belongs to the calcareous ooze area. In this area, the average metal values are quite higher on carbonate free basis because of the dominance of the hydrothermal activity. As the sediments have been raised much above the carbonate compensation depth, so the metal contents are very much diluted by the biogenic activity. The iron by manganese ratio is 3.29 and the iron plus manganese by aluminum ratio is 60, which clearly indicates the dominance of the hydrothermal components. The copper plus nickel by manganese ratio is 0.015. The area B sediment lies further south of the previous area and is also calcareous in nature. Here also the metal values are high, but not as high as the previous area. The iron by manganese ratio is 9.64 and the iron plus manganese by aluminum ratio is 11.93. The copper plus nickel by Mn ratio is 0.044. Now, we have tried to calculate the sediment fractions for average sediments from areas A and B. First, we have discussed on non-carbonate free basis. In that case, you see that the biogenic component, calcium carbonate component in both areas are nearly 48% and 66%, and the metalliferous sediments are nearly 50% and 30.49%. So, then the sample was treated with H2O2 in order to remove the calcium carbonate content, and it is again recalculated, and it has been found that in area A we have the metalliferous sediment content up to the order of 93.35%, whereas in area B it is about 80%, and the pelagic clay is only 6.81 in area A and 20% in area B. This is a very important figure. At the x-axis, we have aluminum by aluminum plus iron plus manganese, whereas at the y-axis, we have iron by titanium. The upper curve shows the composition of the continental crust, and the lower curve shows the composition of the tholeiitic basalt. And the vertical lines, inclined lines upon these areas indicate the contribution of the hydrothermal sediments. If the curve is, the inclined line is touching the upper curve at 70, then in that case, the contribution of the hydrothermal sediment is 70 and the metalliferous crust, oceanic crust composition contribution is nearly 30. Whereas if it is touching the lower line, then in that case, the hydrothermal component is 70% and the oceanic basalt composition is nearly 30%. And if the area is lying between the two curves, then it means that 70% is hydrothermal sediments, and among the 30%, remaining 30%, 15% is from the continental crust side and 15% from the tholeiitic basalt side. So, it can be observed that in area B, we have the hydrothermal sediments from 80 to 90%, whereas in the case of area A, we have more than 90%, approaching nearly 98% or even more of the hydrothermal sediments. This is a very important figure, ternary diagram, nickel plus copper plus cobalt into 10, iron and manganese, and here the several types of known sulfide deposits along the midoceanic ridges are shown demarcated in this area, and our samples are lying near to the hydrothermal Galapagos rift, bore deep sediments, sulfurous iron and manganese oxides, and mid-Atlantic ridge, that is a famous hydrothermal clay. In conclusion, we can say that in the investigated areas of this Pacific rise, the spreading rate is extremely high. Therefore, the magma chamber is at a shallow depth. The seawater in the thollitic basalts of the active ridges is circulated by strong convection currents generated by a thermal gradient between the top of the magma chamber underlying the fractured basalts. The temperature is around 1200 degrees centigrade. This acidic solution thereby picks up appreciable quantities of metals like iron, manganese, zinc, copper and nickel. On re-entry of this solution into seawater, an abrupt change in pH from acid to alkaline takes place, as a consequence of which heavy metals precipitate rapidly as oxides and hydroxides under oxidizing conditions in near bottom seawater. The culmination of these processes results in the precipitation of hydrothermal sediments in these areas, which are now mixed simultaneously with primary carbonate products contributed by planktons, chiefly foraminifera and coccolith in both areas A and B. The dilution of the sediments with carbonate varies with distance from the vent. The sediments, which are now a mixture of biogenic component and metalliferous sediments, are deposited at a very high rates at the ridge. Due to location of the investigated areas far from continental influence and due to high sedimentation rates in these areas, it could be inferred that the detrital contribution is very low. Thus, the overall hydrothermal contributions in these areas A and B are of the order of 95% and 80 to 90% respectively. Once again, in brief, I would like to summarize the entire thing. What happens? The bottom sea water is cold and it is alkaline in nature, and the magma chamber, which is at a quite shallow depth, 1 to 3 kilometers, here the tendency of liquid is always to come up, to rise, and according to the Pascal law, the liquid flows towards the area of least pressure, and least pressure is always upon the surface. So, it tries to come up. During its upward journey, many things happen. That depends whether the magma is more or whether the oceanic seawater percolation is more. If the seawater percolation is more, then the activities is of different type. But anyhow, the oceanic water is percolating through the vent, and this oceanic water, which is cold and alkaline, mixes with the magma that is hot and acidic, and as a result of that, the temperature of the oceanic water rises, and also at the same time the condition, that is prevailing condition, that is from alkaline it becomes acidic. Under this changed environment, it picks up many things into solution from the magma, and by that time it once again becomes cold and it tries to come up. While it reaches to the surface of the sea floor, it is once again mixing with the alkaline seawater, cold alkaline seawater, and as a result of that, under this changed circumstances, whatever the metals which have been brought into solution, they are precipitated along the sea floor, and as a result of that, if they are reaching to the surface of the sea floor, we are getting the massive oxide deposits, and if they are not reaching to the surface of the sea floor, remain confined within the sea floor, then in that case, because the condition is reducing, so we are getting the massive sulfides like chalcopyrite, galena, sphalerite, etc. Thank you very much. Mid-oceanic ridge is really a very good potential for the present day exploration and extraction program, and fortunately the Papua New Guinea has already started mining in that area, but still we are looking forward to adopt the technology which can do more and more mining in these areas. Unfortunately, along the Indian Ocean and within the territorial zone of India, we do not have such deposits where because of the absence of the active ridges. The 90-degree ridge is there, but it is inactive ridge which is highly diluted, and there the metal concentration is negligible. Thank you very much.